Welcome to the course on design of power electronic converters. We were in the module of power semiconductor devices and we had started discussing MOSFETs. Today's lecture we will be looking into the switching characteristics of MOSFETs. To understand the switching characteristics of MOSFETs, the type of circuit that can be used is shown here. So, what you see, this is the one leg of an edge bridge, and here this diode, this body diode of the MOSFET is shown explicitly. Now, this is the device under test, that means this is the MOSFET for which we want to study the switching characteristics. So, if we want to study the switching characteristics of this MOSFET, we do not want to allow this MOSFET to conduct, and so this is turned off by giving a negative voltage between the gate and source. So, now the way this circuit functions is that there is a DC supply over here and current flows through this inductor, and then it flows through the MOSFET whenever the switch is on. This gate pulse is high, and whenever this gate pulse is low, that means let us say if you are applying a negative voltage between gate and source, then the current will be freewheeling through this diode, because there is already an established current in the circuit, and so it will be freewheeling through the diode. And this is the notation that we are going to use, that ID is the current from drain to source and VDS is the drain to source voltage, and VGS is the voltage between gate and source. Now, to drive it, we can draw an equivalent circuit in this manner, that there will be a gate resistor RG which will be connected to the gate of the MOSFET, and there is a driver which we will be discussing later, which is going to drive this gate to source region. So, this is represented over here with a pulsating voltage source, and it is denoted as small Vg, and let us say the voltage that it goes to maximum is capital Vg. Now, the way the waveforms we are going to obtain. So, this is your gate pulse that is shown here, that is the gate pulse which is given over here to the gate to source, and then there is the inductor current, there is a slight increase when the MOSFET is on. So, the voltage across the inductor at that time is equal to VDC, because this MOSFET is on. So, this we can assume it to be like short, because these waveforms, these are drawn for your ideal MOSFET. So, the current over here will increase slightly when this lower switch is on, and then when we turn off this lower MOSFET, at that time what will happen is that this diode will start to conduct, and so this MOSFET will be blocking, and during this time this current is freewheeling. So, it will, this inductor current will reduce slightly. Okay. So, this is the inductor current waveform that we will be observing, the nature of the inductor current waveform. And what will be the nature of voltage and current waveforms through the MOSFET? So, when the MOSFET is not conducting, it is off, it is going to block this voltage of VDC, and that is what we observe here. And when the MOSFET is conducting, at that time it is going to carry the inductor current. So, it is same as this current IL, that is what we observe here. Now, this is the point at which the MOSFET is going to turn off. So, this is the turn off, and this part is the turn on, and what we observe is that here when it is turning off the MOSFET, the diode is going to turn on at that time. And here when the MOSFET is turning on, at that time your diode turns off. Okay. So, that also means that while your MOSFET is turning on, there will be this diode turn off it. So, there will be an influence of this diode turn off characteristics while the MOSFET is turning on, because we have studied this before that your diodes, while it is turning off, it has got the reverse recovery current, reverse recovery charge is associated with it, and so that effect we should be expecting to see while the MOSFET is turning on. So, let us look into the switching characteristics of MOSFET now. So, this shows the switching characteristics of MOSFET, and this is somewhat an approximated waveform. Do not think that you will be seeing exactly this kind of a theoretical waveform when you do perform the experiments, but more or less this is what is going to happen when you perform the experiment and you switch the MOSFET. So, that is what we will see now. So, now let us say your VGS, this is going to begin at this point. So, from here to here, this time period, this is your VGS voltage, gate to source voltage, this is the drain current, and this is your VDS voltage, that is voltage across the MOSFET. So, this is where the gate to source voltage begins to increase. So, what we observe during this period, neither the current changes nor the voltage changes. So, there is a delay, and at the time this VGS increases and it reaches the threshold voltage over here. So, this is the voltage VTH, threshold voltage. Up till then no current will increase, no change will happen. So, there is a delay in the turn on. So, this period we can call it as TD on. Next, what happens is this interval, when your this current starts to increase as the voltage, gate to source voltage increases above the threshold voltage, and it reaches to this point which corresponds to your Miller voltage or the Miller effect. So, this is given as the name VGS PL. Many times this is denoted like this, it may be denoted in some other way also, but this is basically the Miller voltage. So, during this time period, it is the current which is going to increase, and this current, this time period we can call it as TRI. After that, what happens is that your voltage tends to decrease, and this gate to source voltage over here is remaining constant, it is not increasing. One thing you also notice here, that before this, when it is going from threshold to this Miller voltage, although the current increased, and it actually increased and reached to a value greater than the on state current value, which is this drain to source voltage did not change at that time. And now why is this current higher than what this your turn on state MOSFET current is going to be? This is because the diode is also turning off at that time, and this is associated with the reverse recovery current of the diode. So, this part is your reverse recovery current IRR, and this time is your TRR, reverse recovery time. Now, when this Miller period is going on, at that time what happens is that your current, of course, there is not much change, is basically the reverse recovery current which is reducing, but the voltage, there is a huge change. The voltage goes from what was the off state voltage to almost very close to the on state voltage drop. You can see this part, it almost goes very close to the on state voltage drop, and this period is many times denoted as TFV. Further, what happens is this, that your whatever is the voltage which has to finally is left out, that means this VGSPL and what is the difference between your final voltage the voltage source is providing, which is what we had denoted as capital VG, that is what is further increased, and during that period it is this increase in the voltage that is you will be observing in the gate to source voltage, and your current is has reached to the on state current value before that, only before that period, and the voltage just finally goes to the on state voltage drop. So, by this time actually, by this time your Miller period is over. This is your Miller period. So, by this time the Miller period is over, your turn on process is completed. So, this one is your VDS on, the on state voltage drop, and this is very much contributed by the on state resistance, and this part is your IL inductor current value, which the on state is the inductor current during the on state what is going to conduct. So, your on time period then can be written as equal to TD on plus your TRI plus your TFV. Then further this continues to remain on while the gate pulse is there during this entire time, while the gate pulse is there. So, this is on. So, this just continues. After that, let us say now the gate pulse is removed and it starts to turn off. So, when it starts to turn off, let us see what happens. So, initially what happens is that your voltage, gate to source voltage, it goes down from VG to VGSPL, that is your Miller period, Miller voltage. And during that time what you observe is that there is a slight increase in the voltage and the current almost remains same. So, you can say that kind of no change. And so, this is the delay time, and we can write it as this as TD off. Further, what happens is your this Miller period continues during this time, And at that time what we observe is that the current does not change, it remains where it is, but the voltage builds up. The voltage builds up and there is a shoot through in the voltage. It goes above what it is supposed to block. So, there is a rise in the voltage and almost no change in the current. So, this time period, it can be denoted as T or V, rise in the voltage. So, the Miller period gets over by the time. After that, your this gate to source voltage starts to reduce and it reaches the threshold voltage, and during this interval what happens is that it is your current which starts to come down and almost becomes close to the leakage current or the offstate current, this current. And this can be denoted as your this interval, your T Fi, the fall in current. And by the time what happens is this your this shoot through also comes down and it settles close to the blocking voltage, what the MOSFET is supposed to block, which is equal to your VDC. So, what we observe from this, that your off state, what happens when it turns off is almost the opposite of what happens when it turns on. When it turns on, there is a delay and then first current rises and then voltage decreases, and when it turns off again there is a delay and it is the voltage which builds up first and then it is the current which comes down. And what we also observe is this, during this interval, during these two intervals maximum losses are going to take place because both your voltage and current are going to be high together. Now, what is the reason of this shoot through? This overshoot is basically because of the stray inductances that are present in the circuit. Your stray elements are there which also lead to your shoot through in the voltage, overshoot in the voltage. And your turn off time is basically contributed by this TD off and these other two intervals, your TRV and your this interval which is your TFI. So, T off, you can write it is equal to TD off plus TRV plus TFV, and this is this TFV. Now, what are the notations which are given in the data sheets related to switching characteristics of the MOSFET? So, your total gate charge that is provided as you are turning on and turning off the MOSFET, then I mean basically you are charging the three capacitances that are involved in it. You may recall this we had a look into in last lecture. So, this is your MOSFET and then you have this capacitor which is your gate to drain, then this one which is your gate to source and this part which is your drain to source. These three capacitances, they have to be charged and discharged while the turn on and turn off process are going on. Now, I did not explain you here that which capacitance is becoming is getting charged or discharged when it is turning on and when it is turning off, but we will be discussing it later again when we discuss gate drive circuits. So, here I just wanted to tell you that what is the nature of the turn on and turn off waveforms. So, as these capacitances are turned on and I mean basically charged, they are charged and discharged, there of course there will be a charge associated with it, and so those are given in the data sheets, your total gate charge, then gate to source charge which is associated with this capacitance CGS, and then gate to drain charge which is the Miller charge, and that is your CGD. Then this turn on delay time TD on, this we just saw, so that is what is provided in the data sheet many times. Then TR is also specified, and the way many of the application notes they define it as the time between when the drain current rises to 10% of the maximum value at MOSFET turn on and when drain to source voltage drops to 10% of maximum value. So, that means this TR, it is your sum of your this that we just saw, that your TRI plus your TFV. Then your other times which are specified in the data sheets is your TD off, turn off delay time, that is also we just saw, and TF your fall time which is the time required for drain current to drop from 90% to 10% of maximum value. Okay, this also we just saw in the switching characteristics. So, these are mostly your notations which you will find in the data sheet, and we just discussed it now. Then notations related to body diode, your reverse recovery time of the diode, and your QRR reverse recovery charge associated with the diode, and the forward turn on time. This sometimes may be given, sometimes may not be given. Some data sheets will also be giving you the maximum reverse recovery current, and forward turn on time also some of the data sheets will be providing, but most of the time, as I had told you before also, it is the turn off time which dominates for diodes. So, what are the key points of this lecture? So, there are gate charges and associated capacitances which play the role in the turn on and turn off process of the MOSFET. And what is the usual sequence? The sequence is that first there will be a delay, then there will be a rise in current, and there will be after that a fall in voltage, and exactly the opposite sequence follows when the MOSFET gets turned off. And the body diodes turn off characteristics that affects the turn on of the MOSFET. Thank you.